Hi all. In a previous video, we had learned about this very interesting technique of unsupervised learning called the K-means clustering, where given a set of input data points which are unlabeled and K clusters which they need to be classified into, the objective was to classify each of the given n points into K clusters. Now again, remember the important point there was that the points were not pre-labeled, so we had no clue which particular cluster or label each given data point belonged to. And using the k-means clustering algorithm, which is guaranteed to converge, we were able to assign a cluster to each data point in a very elegant manner. So this works very well in many situations, but there are some situations where this does not work very well. And one simple example is, as you can see on your screen, is that of the case where the data set is unbalanced, meaning that there are a lot of points belonging to one particular cluster and a few points belonging to another cluster. And since the k-means clustering algorithm is very simple and uses just the Euclidean distance of the input data points from the cluster centers, the misclassification rate could actually be significantly high. And as you can notice in the k-means clustering algorithm, each cluster boundary is a circle centered around the cluster mean. Now this also may not be valid in some situations where the data could be actually skewed and the circular clusters may not be able to work properly, as you can see in the example on your screen. So now to handle these two kinds of problems, we have a new method, or rather not something that is new but something that is different, which is called the Gaussian mixture models. So here what we do is that we have these different clusters, as you can see on your screen. So instead of just identifying their center and then drawing a circle around them, we actually model them as Gaussian distributions. And because you have different center points and each cluster has its own variance, so you have a mixture of Gaussians. Instead of a single Gaussian, you have a mixture of Gaussians where each Gaussian has its own mean and own variance. So essentially what we have is that we have some, again, n data points labeled xj, where j is going from 1 to 3 and so on up to capital N. You have k clusters denoted by Ci, where I is going from 1 to 3 and so on up to capital K. And now instead of just assigning a cluster label to each data point, what we estimate is the probability of the data point belonging to a cluster. So as you can notice in the k-means algorithm, we did a hard assignment of a cluster label to a particular data point. But now we are not doing a hard assignment, but finding the probability of a given data point belonging to each of the clusters. And this we do using a mixture of Gaussians because each cluster has its own separate distribution. So the probability of a given data point belonging to a particular cluster Ci is modeled using the Gaussian distribution, which of course is determined by its mean, which is the mu I, and the covariance matrix. So when you have a single variable Gaussian distribution, then you have mean and a variance, which are scalars. But when you have multiple variables, then you have the mean, which becomes a vector instead of a scalar, and this variance becomes the covariance matrix. So this is a multivariate Gaussian distribution, and its expression is this is equal to 1 divided by root over of 2 pi to the power of k, determinant of the covariance matrix, exponential of minus half xj vector minus mu I vector. You do a transpose, the covariance matrix inverse times the xj minus mu I. So this notation might be slightly confusing because we talk of transpose only for matrices, but here we have vectors. So remember that here the representation of vectors and matrices is interchangeable. So it doesn't really matter as long as you understand what is it that you are doing. So now this represents the probability that a given input data point belongs to the cluster Ci, which has the mean point mu I vector and a covariance matrix given by sigma I. And now what we have to begin with are only these data points xj because it's an unsupervised learning algorithm. And of course we have the number k also, that how many clusters you want to divide your input data into. But this mu I and sigma I is something that we do not have and which we need to estimate. So how are we going to estimate that? So in order to do that estimation, we need one more variable, which is phi I, which represents the fraction of points belonging to Ci. Now this phi I is computed in a slightly more non-trivial manner. It is not just the number of points in class I divided by the total number of points, because as you know that in the Gaussian mixture model algorithm, we are not doing a hard assignment of the data points to the classes, and we are only computing the probabilities. So this phi I is not just a ratio of two numbers, but is calculated a little more differently, which we are going to see very soon. So for solving this problem, which means to estimate the values of mu I, sigma I and phi I, we use the expectation maximization algorithm, which we had learned in another video. So in case you haven't watched that video, the link is available in the description box, and I very strongly recommend that you watch that video before continuing further, because an understanding of that expectation maximization algorithm will help you in properly understanding what we are trying to do. And the expectation maximization algorithm is required because analytically solving for this mu I, sigma I and phi I is almost impossible in all practical situations, and that's why you need to use the expectation maximization algorithm, which is an iterative process, and the beauty of the process is that it is guaranteed to converge. That is very, very nice. Now again, the convergence may be to a local minima, but at least there is convergence. That is a nice thing to have. So let us first see the expectation maximization algorithm in brief, and then we will actually go into the elaborate mathematical details. So we have the expectation maximization algorithm for the Gaussian mixture model. So what do we have over here? So firstly, as you know that the expectation maximization algorithm consists of two steps. One is called the E step or the expectation step, and secondly is the M step, which is the maximization step. So in the E step, what you do is that you use some value for phi I, mu I and sigma I, which I will tell you how to initialize. Using these values, you estimate the probability of Ci given xj. So now what does this mean? What does this mean is that for each given data point, you find the probability of the class that it may belong to. So Ci so here I takes k different values. So for each data point you compute k number of these different probabilities using these values. Now the next comes the m step, which is that using the assigned, or rather the weighted Ci for each xj, you update your values of phi I, mu I and sigma I. So I hope you can understand what we are doing. So you have some initial values for phi I, mu I and sigma I. Using that, you estimate the probability of each data point belonging to a particular cluster or a particular class. Now once these probabilities are calculated, using this you update your value for phi I, mu I and sigma I. Now here again remember, we are not going to pick up the class for which this probability is maximum. We are not doing that. We are leaving it as a probability estimate, because in the Gaussian mixture model we are doing a soft assignment. In the k-means clustering algorithm we did a hard assignment where we said that this data point belongs to this cluster, but here we are not doing that. We are only computing the probability. Now of course at the end of this algorithm, when it has converged, you can go ahead and do that hard assignment at the end, but that is only for practical purposes. As far as the algorithm goes, hard assignment of the clusters to a given data point is not required by the algorithm, and that is why this algorithm works better than the k-means clustering algorithm. Now of course all this heavy computation makes it much slower, but when required, for problems where k-means algorithm does not work, there you definitely have to take recourse to this Gaussian mixture model. So this was a brief idea about how this EM works, and now let us get into the murky details and see what exactly you need to do to make this expectation maximization work. Now once again let me emphasize, this EM algorithm is guaranteed to converge, although the convergence may be to a local minima, but convergence is definitely going to happen for sure. So for any of such iterative algorithms to begin, the first and foremost step is your initialization. So to begin with, you only have the data points and the number of clusters, but what you also need are the phi I, mu I and the sigma I values. So that is where you start, and then you iterate till you reach convergence. So for the mu I, so you begin with mu I, so you randomly pick the mu I. I am sometimes omitting this vector notation, which I hope you remember what it means, that mu I is a vector. So randomly pick mu I from the unlabeled input data points. So you have capital N number of data points. Out of those capital N number of data points, you randomly pick capital K number of points and assign them to be mu I. Now the nice thing is that it doesn't matter which initial points you pick, your convergence is definitely guaranteed. For each of these points mu I, you compute the covariance matrix by using the entire data. What does that mean? That for each point mu I, you assume that the entire data belongs to that particular cluster, and then using that you estimate your covariance matrix. So compute the covariance matrix sigma I using the whole data set for each mu I. So now once you have done that, you have your initial mu I, you have your initial sigma I, and finally what you need are the phi i's. So you set your phi I to be simply 1 by capital K for all I. So you say that all the points are kind of equally distributed everywhere, so you don't worry about it and you just uniformly distribute your points. Now this is one of the ways of initialization, which is very crude. You could also use the k-means clustering algorithm to do the initialization, which actually makes your process much faster and often leads to better results also. So instead of initializing using this brute force simple algorithm, run the k-means algorithm, find the mu i's, and then using that estimate the sigma I for that particular cluster and the phi I using the hard assignment in the k-means algorithm. And then from there you start and then apply the Gaussian mixture model, which often works much better and also leads to considerable speed up also. So for example, in this given figure, instead of starting from scratch, you could use the k-means to reach up to this point where the misclassification rate is high and then apply the Gaussian mixture model algorithm to do the classification properly. So now earlier we have seen the E step and the M step in sort of intuitive manner. Now let us write the actual mathematical expressions and see how they look like. So now we want to understand the E step, or what is the expectation step. So here what we estimate is the value gamma ji. So what gamma ji represents is in some sense the fractional allocation of a given input data point to a particular cluster mean. So as I said, in the k-means algorithm, we did a hard assignment. We said that a given data point belongs to a given cluster, but in the Gaussian mixture model, we do not use this hard assignment, we do a soft assignment. So what we ask is that for a given data point, what fraction of the assignment should be to cluster point 1, what fraction of the assignment should be to cluster point 2, and so on. So that is a weighted manner of assigning clusters to a set of given data points. And the expression is equal to phi I times the distribution xj given mu I comma sigma I divided by sum over all i's. Phi I normal xj given mu I and sigma I. So this will give you the fractional assignment of a given data point to a particular cluster point, and this essentially is the probability that your given data point xj belongs to the cluster ci, and as we mentioned that this is what the E step is all about. Now using this computation of the probability that your given point xj belongs to the cluster ci, what we need to now do is the step M, or the maximization step, where using this you update the value for mu I, sigma I and phi I. So again we begin with mu I over here. So now we have the M step, and to begin with we update the values for mu i's, which is nothing but 1 by ni. I'll tell you what ni is, don't worry. Summation over all j gamma ji times xj. So this is again similar to the k-means algorithm, where the cluster means or the cluster center with just the mean of all the points belonging to that cluster. But in the GMM algorithm, because we are not doing a hard assignment, so the mean is computed using the weights. So in the k-means clustering algorithm, here we had rji, which was either 1 or 0, but here this gamma ji is a fraction which can take any real value between 0 and 1. And what is this ni? This ni is nothing but summation of gamma ji over all j. So this basically represents the effective number of points in the category Ci. So in the k-means algorithm, Ni would be an integer, but in the GMM algorithm, Ni is a fractional value. So now we have computed our mu I. So then we go ahead and compute our sigma I, which is the covariance matrix and given by 1 by Ni summation over all j gamma ji into xj minus mu I into xj minus mu I transpose. So this is the way a multivariate Gaussian distribution is defined when you have multiple variables. If you have a single variable, then this will reduce to your regular expression for the variance. So now your mu I and sigma I have been determined, and finally what we need is phi I, which is simply given by Ni divided by n. So now remember that here in this expression, when you use mu I, use the updated value of the mu I from this step and not the mu I from the previous step. So now this is your m step. So now you have your e step and you have your m step, and what do? You iterate in a loop till you reach convergence. Convergence means that these values for mu I, sigma I and phi I need to stabilize. Another option is that there is something called the log likelihood function, and you can iterate till your log likelihood function is again stabilized. So what is this log likelihood function? This is given by summation over all j logarithm of summation over all I phi I times the Gaussian of xj given mu I given Ci. So basically what you're trying to maximize is the probability of assignment of the points to various clusters. If they have been assigned correctly, then this log likelihood will be maximized. So either you can carry out your iteration till this log likelihood reaches some stable value, or you can iterate till your parameter values mu I, sigma I and phi I converge to some stable value. So this is the Gaussian mixture model algorithm, and as you can see, it has some clear advantages over the k-means clustering algorithm. So now let's just summarize the important differences between the k-means algorithm and the Gaussian mixture model. So you have the k-means clustering and the Gaussian mixture model. And the first and the crucial important point is that in the k-means clustering algorithm, you have a hard assignment of Ci to each xj. But in the Gaussian mixture model case, you have a soft assignment in the form of your gamma ji, which is actually a fractional value between 0 to 1. Secondly, because in k-means clustering algorithm you are doing a hard assignment, so this is considerably fast. So here you have fast convergence even for high dimensional data, but the EM algorithm is slow, especially if you have several clusters and several input features. Then your expectation maximization algorithm can be fairly slow. One limitation of the k-means clustering algorithm is that it assumes the clusters to be spherical, but the EM does not make any such assumptions and can handle more complex shapes or other decision boundaries. And finally, the k-means clustering algorithm is much easier to interpret, meaning that you either say that a point belongs to cluster 1 or cluster 2 or cluster 3, so there is no ambiguity. But here, because you have these gamma values, so this can be slightly difficult to interpret. But still, although the Gaussian mixture model has some of these limitations, but because it does a soft assignment and because it computes the actual probability distributions, it can be very, very powerful provided you have the required computational resources to do the necessary calculations. So I hope this gave you a good idea of the Gaussian mixture model and how does it compare with the k-means clustering algorithm, and I very strongly recommend that you actually code it using Python and see the results for yourself, because learning theory is one thing, but to really understand what's going on you need to do the coding yourself, and that is when you will really begin to intuitively understand what this algorithm is trying to do.